Okay, so we've got this rotating beam. That's what we've been looking at. That's the red point, the red chalk right there is pointing at us when? Now. Now. Okay. As I said before, everybody's now will be at a little different time than everybody else's. Depends on how your brain is wired. It depends on your experience with timing things. But there it is. And we're going to keep the video on this as we make our marks. Okay, I'm going to get this thing spinning, then I'm going to go run over and start the tick-tocks. Got a question? Okay, we're going to get this started, and then in a few seconds, I'll start tick-tocking. Ready? Tick. Tock. 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 Okay, it stops. You know, something about being a clock makes my neck stiff. Okay. There we go. Now you notice the thing is in retrograde motion. Okay. It's come almost a complete revolution backwards. And now you might or might not be able to see it. You'll be able to see it now. It's oscillating, just like that pendulum oscillates. And the mathematics of that oscillation is very much like the mathematics of the pendulum oscillation, and that's something that we'll be able to measure. And the reason it's oscillating is because one end of this is essentially heavier than the other end. Okay, you got more mass on one end than the other. Okay. Which means that at, let's say, this position, it's got less gravitational energy than it does when it's at the opposite position. It's called gravitational potential energy. Gravity's trying to pull it down, but right now it's as low as it'll go. If it's at the opposite end, gravity pulling it down will cause it to come around and end up here again, roughly. Friction has a little bit to do with that. But it's at this position, it's got enough angular momentum to keep going. But friction is sucking energy out of it, so it's not going to go all the way back to where it started. Now it's going to come back. And the period of that motion, the time it takes to go from there to here, and then from here back to here, should theoretically be constant, just like the period of a pendulum should theoretically be constant. So those are things you kind of want to think about, but we have to develop those ideas. We have to develop a mathematics, which is simple first semester calculus, okay? Nothing beyond that. But we do have to understand that first semester calculus. And then we have to be able to relate it to the physical world. We have to intuitively understand the physics. So the intuitive understanding of the physics that's related here is just that basically the mass of this system is on the average lower at this position than it was at that position. And gravity wants to pull it to the lowest possible point. Now, if I take the frame away from it, gravity will pull it straight down, right? At least until it hits the table. Take the table away, it'll take the floor away, concentrate the earth to the size of a marble, and it'll keep accelerating until it hits that marble, right? And the acceleration is going to increase because the closer it gets to the center of the mass of the earth, greater the acceleration. That's an inverse square thing. So these are terms that I'm throwing out now because you want to have them in your mind and maybe think about them to some extent, because most of you haven't had high school physics, and your high school science class probably didn't even measure, or your junior high science class didn't even mention inverse square, because half the class can't begin to think about it. And you can't talk about anything that the whole class can't understand. That's the way I kind of visualize it. Other advantages of doing that too, you want a literate society, but I think we've gone too far in one direction. Well, actually, let's go back to the board so I can point to it. Okay, now the question was, what if you have one of these that occurs right on a tick? So let's say you go a few more ticks. So you annotate it like that, okay? Would you count this tick or not? So I'm going to say, just for convention, so everybody does the same thing, count it. They got to be consistent. If you're doing this yourself, that's an arbitrary choice. If it was pretty much right on it, but you perceived it was a little early or a little late, you can move that tick over a little bit or over a little bit, but still above the check mark, okay? But if you didn't perceive that, just put it there and count the tick. And if you put it a little early, then don't count it. That won't make much difference. Once you get your graph, you can see what difference it would make if this was actually early versus late. Okay, in other words, if you put this point 1 unit to the right or 1 unit to the left, it's not going to make much difference in the trend of the graph. If you got, I don't know, how many ticks did you get on that one? That probably went for a couple minutes. You probably had 50 or 60 ticks there, at least. Okay, so you got a graph of 50 or 60 ticks being off by 1 tick when it's really not a full tick anyway, is not going to make much difference. This tick could have been right after the second, or this revolution could have occurred either right after or right before, right after the second tick or right before the third tick. We don't know. If they're in between, we could make them all 2.5. Then we're pretty sure that we're not off by more than 1/2. But those differences are just going to get absorbed in the quantity of data you have and won't make any significant difference in your theta function. Okay. Just probably third significant figure in the main coefficient of your theta function. All right.